jump in as they reach. Okay, right, so you can start. Okay, so evening. I hope you all are well, and I hope you all at least looked at Lab 20. And tried something. As I said before, let me know if you're stuck anywhere, or if you have any questions about it. I really couldn't find a better lab for it. I wanted you to learn about the whole automation stuff in the context of Cisco, because that's what we introduce in here. And the only place I could get a lab like that working is in that sandbox that the lab describes. So if you're interested in it and you want to do more stuff, just look around in the Cisco DNA Center sandbox labs there. Some of them you have to request a session, so you have to like schedule a lab session, and then you could only log in. They'll give you credentials, and you could only log in during certain hours. Others they call always on sandboxes, so they basically have an appliance or a VM, and it's always running, and anybody could log in and play around with it. But the write, well, they only have read-only access mostly. So the ones that allow you to write and actually change stuff, those will be scheduled, because obviously can't have too many people logging in and changing stuff at the same time. So yeah, take a look at the Cisco DevNet sandboxes if you're interested in this stuff at all. And if you're really interested in it and you want to know this whole automation chapter much better, then I recommend going down the DevNet track. It seems to be fairly interesting. The only risk there, I guess, is like I said last class, I don't know anybody who implemented this kind of stuff in Trinidad at least, or even in the region yet. This stuff is really expensive. Cisco stuff is just expensive on the whole, and it doesn't bring a ton of strengths yet. So realistically, when people need to put out this kind of CapEx, they need a ton of justification to say, hey, we need to upgrade to this Cisco DNA Center appliance because X, Y, and Z. So I will show the advantages that Cisco promotes so far, but realistically in the Caribbean, I can't honestly tell you that people have been adopting it yet. But the whole purpose of it is to prepare engineers so that whenever they do adopt it slowly, we'll know what to do, right? So it still makes sense to learn it. Right, so last class we finished up security, and I'll do a quick review of what we did in the last week. And we basically finished up this chapter 5 here, and we started chapter 6. So we started the explanation of what automation does and how it can help us, and then comparing traditional networks with controller-based networking. So we introduced this concept of a controller and moving the control plane basically to this centralized controller as opposed to running all our nodes independently. So I'll do a quick recap of that, and then we'll go into some a deeper dive of some of the separation of the control plane and the data plane and these APIs, and this thing called overlay and underlay networks and stuff. So it'll be kind of technical, but not that bad. So we're gonna split up the remainder of the classes into 2 sections basically. So I'll start off with these topics today, and we'll finish up on Tuesday. Right, so just one more presentation to go. We're on presentation 13 here. Right, pointer. Cool. So let me go. Right, so we're gonna continue our description of controller-based and software-defined access architectures. But we'll introduce software-defined access in this class really. And then we'll continue the comparison between Cisco DNA and the traditional networks that we discussed up to this point. And we'll get into some REST-based APIs. So we'll discuss APIs more, because I know a lot of you will still be very confused about what APIs are and how they're useful and stuff. So we'll really get into a deep dive on that. And then in the next class, we'll go through some different configuration management mechanisms. Besides copy and pasting configs, what other mechanisms are there? And then how to interpret JSON encoded data. So what is this thing called JSON, and how can we read JSON data? Right, so first, a brief recap of the last class. So we started off the last class discussing some AAA concepts. So we mentioned that authentication, which is the first A, is the process of verifying who a user is. So authentication, in general, authentication is just verifying who you are. So who a user is by checking usernames and passwords, SSH certificates. You use it with email addresses a lot. So you'll see, log in with Facebook or log in with Google. And all of that is authentication, just verifying you are who you say you are. So what's your username? Prove that you are who you say you are by supplying the correct password for that username. Or now we have newer mechanisms where you might need to pull up your phone and unlock your phone and then press yes to prove that you are who you say you are. Then you have authorization, which is the process that decides what a user can do. So what commands they can and cannot enter on the device, etc. Um, this means the username you have supplied is only allowed to run ping commands in this network. No other commands are allowed. So you could limit what a user is authorized to do. So after they prove that they are who they say they are, then you could say, okay, you are definitely John or Mary or whoever it is. We have authorized John to perform show commands or perform only 2 config commands, nothing else, so that we limit the amount of risk on the network. Then we have accounting, and accounting is the process of recording exactly what a user does while they are connected to the network. So we could say, John logged in at 12:04, he ran these 2 commands, and then he exited out without checking the network, the health of the network, or without checking the interfaces and the bandwidth or any of that. Or he did check the bandwidth and it was good at that point, and it only failed 2 hours after. So when we look through logs, we rely on this accounting to see what the user did at a certain point in time. Right, so we then moved on to discuss some common wireless security protocols, so security protocols used in the wireless network. We first discussed the WEP protocol, which was introduced with the first generation of 802.11 protocols, but was quickly deprecated because of its vulnerabilities. So just in case anybody doesn't know the word, deprecation is a software term, really. I haven't seen it used anywhere else. And it basically means something is old or something should not be used. Usually it's because of a security vulnerability or some flaw in a function that will say, okay, you can still use this, but we highly recommend that you don't. So let me see an example. Okay, right now in the CCNA, you know about Telnet and you know about SSH. So you know on a Cisco router or a Cisco switch, you can't set up Telnet and you can't set up SSH. In the software world, they would have said Telnet is deprecated, which means we highly recommend that you don't use it, and you all know why we don't use it now, but it is still possible for you to use it. It's just we highly recommend that you don't use it because of XYZ, and we suggest that you use this thing as an alternative. So in this case, the thing would be SSH. That's the alternative. So in this case, WEP was a security vulnerability, so it was deprecated. And then we moved to the WPA protocol, which was introduced as a replacement for WEP in 2003. So WPA brought more strength due to the use of TKIP and a MIC. So remember all these security protocols that we introduced, and we mentioned the various weaknesses of them. So WEP had that fixed initialization vector, which meant that you could quickly capture frames on the wireless network and build up the security key and sort of brute force your way into the network because of that fixed vector, whereas TKIP was temporal based, so it's time based. So that initialized vector changed with every frame. So however, WPA was also found to have a high number of vulnerabilities and was replaced by WPA2 in 2004. WPA2 brought even stronger security due to its use of AES and CCMP. Now in 2018, to keep up with this improved compute power of modern machines, WPA3 was introduced with AES and GCMP support, which provides increased strength through longer key lengths. So as the power of CPUs and GPUs have gone up, people have been able to brute force even the better protocols like AES and CCMP. They have so much stronger computers now that they could just brute force these passwords in a matter of minutes or hours or days, depending on how good their dictionary attacks are and all of these things. So to continually evolve the security and make sure it is still secure, you need to bump up the key lengths and make sure that these protocols could use these longer key lengths, which is what AES and GCMP introduced in 2018. So we then moved on to configure a basic WLAN network using WPA2 PSK security on a Cisco wireless LAN controller. This configuration was performed entirely using a GUI with the password configured simply as a pre-shared key, so that no external AAA configuration was required. Even though we followed Cisco's exam guidelines, we saw how simple it was to configure other options. For example, we could use WPA instead of WPA2, or we could use 802.1x through the GUI. So through the GUI, you saw a page like this, where we could just toggle around parameters very easily. So we could just put this drop down here, and let's check or uncheck our box. We could move up from AES to GCMP just by unchecking this and check this. Or we could include TKIP by checking both at the same time. We could research all these other parameters and enable them just by checking our box here. So this GUI is fairly intuitive, and it's very easy to apply these settings. So just check it and click the apply button that would be here in the top right somewhere. Right, so we then started discussing an entire mindset shift from a traditional network topology into a controller-based network topology. So we started by discussing some of the common problems that we experience as engineers using traditional networks, such as mistyping commands, difficulty in copying and scaling configurations across a large number of devices, and the high amount of time taken to manage all of these devices independently. We then discussed how we can group the general functions of our infrastructure devices into two main groups or planes, the control plane and the data plane, and centralize the control plane for many devices into a single controller. And we said this was very much like when we move the access points from being autonomous access points and functioning by themselves and existing in a bubble by themselves, and we pulling off as an alternative to that, we pulled off the control plane and centralized that control plane so that we could control multiple APs from a single controller. And we said this is very much like that, just on a larger scale. So we then discussed some of the changes that we would experience by managing devices from a central controller as opposed to managing them independently. So this is what we said, right? We had all these network devices that used to be managed by themselves before. We used to just SSH into these things and put in our commands, run OSPF, whatever it is, copy and paste the commands, and all of these devices operated independently. And what we did now is we took off the control plane here, which is just suppressing some functionality, and we let this controller manage this control plane functionality through these interfaces called southbound interfaces. And we left the data plane here so that the network devices were really just devices to forward packets. They did that packet forwarding process, but there wasn't much intelligence on them. We moved the intelligence to the controller there. We ended the last presentation by comparing some of the differences between these two types of networking. We discussed how configurations could be compiled in a central location and pushed from the controller to all devices, instead of copy and pasting configs. We also discussed how the controller could help us with IP address allocations, instead of us having to manually assign addresses to each device. Controllers could also automatically implement ACLs on multiple devices according to simpler security policies that we define in them. Lastly, controllers could allow us to perform much simpler scripting, automation, and data gathering from our devices. So all of these are benefits of the controller-based networking over traditional networking. So now let's continue this discussion on controller-based network architectures and introduce a new concept that Cisco calls software-defined access, so SDA. So Cisco SDA is an entirely new network architecture. SDA uses the same controller-based model that we have discussed previously. SDA still groups functionality into two main planes called the control plane and the data plane. So that's what we discussed before. And we centralize the control plane on a node called the Cisco Digital Network Architecture, or DNA Center Controller. So we mentioned controllers before. So Cisco SDA is based around this special controller called the Cisco DNA Center Controller. They don't really include the controller part here, they just call it Cisco DNA Center. But whenever you hear Cisco DNA Center or the Cisco DNA Center appliance or the DNA Center appliance, whatever they call it, just think of a controller. So through DNA Center, engineers make changes through APIs, which are communicating through the northbound interface or through a GUI. However, the southbound interface no longer communicates directly with the independent nodes, which are our network devices that we had before. Instead, Cisco has redesigned this part of the network and introduced the following new networking terms. So before, all we had was the, let me see if I can get back to the diagram. We had this, right? So we said we stripped off all of this control plane functionality and we moved it to the controller. So that's our Cisco DNA Center there. And all that happened was that the controller spoke directly to these network devices through that southbound interface. Right? Now we're shifting it up a little bit and we're saying this part on top here, this network layer is going to change. So those red lines there are going to change. They're not going to be a direct way of talking between the controller and the network devices. So let me discuss that now. So we redesigning that part of the network and we're introducing the following new networking terms. So we have something called the overlay network. So the overlay network is a special network built on top of logical tunnels called VXLAN tunnels, which provide layer 2 connectivity between end devices. So remember, we mentioned tunneling before. We mentioned VPN tunnels and GRE tunnels and those kind of things. And we had the tunnels for the wireless LAN controller as well, which provided that direct connectivity between APs and the wireless LAN controller. So now we kind of exploring that concept or expanding the concept to say that we're using a whole overlay network now, which is a special network built on top of tunnels, and those tunnels are just called VXLAN tunnels. Before the tunnels were called CAPSMAN tunnels, if I remember correctly. So we had the overlay network there. Now we have the underlay network. So we have the underlay network is a traditional, well, is the traditional network infrastructure. So that's the devices, the cables, the connectors, you know, the everything we discussed before. Those routers and switches and fibers and SFPs or transceivers, everything we have in traditional networks. That traditional network infrastructure that provides basic IP connectivity for the overlay tunnels. And then we have the fabric, which is the combination of the overlay and underlay networks, which work together to provide the necessary attributes and features of Cisco SDA. So all we're doing here is we taking our entire network as we knew it before, and we grouping that and calling it the underlay network. So we're taking that network and we're starting to build a set of tunnels over that network. And those tunnels are called VXLAN tunnels. And the combination of all of those tunnels builds what Cisco calls the overlay network. Yeah, so you'll see a diagram here now. So this is what we knew before, right? This underlay network. So we had a bunch of switches, we had fibers or copper between the switches, and we just connected everything together to make up this big fancy network here. So that's what we know. Now we're saying that we're gonna still maintain that network, but we're gonna call this network the underlay network, and then we're gonna set up tunnels between switches, and we're gonna run this thing called an overlay network here. So for example, from switch 1 to switch 2, we're gonna set up a tunnel here, so that switch 1 and switch 2 don't really see these switches below. They just see this tunnel, and traffic will logically pass through this tunnel and go here. So physically, the bits on the wire will still need to pass through, you know, wherever the traffic needs to be, and it will physically go through these connections here in the underlay. But on the overlay network now, we're simplifying it, and we're saying we have a tunnel between this switch, and if a PC here wants to communicate with this PC, it will just come in the switch and use this special SDA architecture to go through this tunnel and come out this switch. So all of this stuff is just abstracted out. Right? So I hope you can understand the difference between the underlay network that we knew before and this new overlay network. So in addition to these new networking terms, Cisco has also introduced some new terms for the devices in this new SDA network. So you have something called a fabric edge node, which is a switch in the fabric that connects to end nodes like PCs and printers and all of this stuff. So fabric edge node like this would be anything that connects to the end devices, right? So that's the end node, your edge node, sorry. Then you have a fabric border node, which is a switch that connects to devices outside the SDA domain. So if you have, you know, if this overlay network is not your whole network, if you only have a part of it where you're trying out this new SDA architecture, and you're leaving the rest of the network untouched, then you would have a border node, which is a switch that connects to devices outside the SDA domain. So you'd have a switch, and you have your SDA domain, which is your new fancy SDA thing that you're trying, and then you have the rest of the network that is outside that SDA domain. Then you have a fabric control node, which is a switch that performs special functions for the underlay network. It requires more CPU and memory than other switches. So this is the control node. This is what's setting up all of this fancy overlay stuff here. All right, so that's called the fabric control node. The use of this new SDA fabric network provides us with many benefits. So why did Cisco introduce all of these new concepts and this whole fancy SDA architecture? So we'll talk about that now. So for example, traditional switching networks use layer 2 links and required spanning tree protocol to block redundant links. They were difficult to configure and maintain properly, and spanning tree issues were commonly seen. In contrast, the underlay switches in the fabric network all use layer 3 links and are fully routed. This means that they are much easier to configure and maintain. It is also much easier to load balance traffic on these fully layer 3 links. So I can tell you, and I'm pretty sure I mentioned it when we were talking about the whole switching, well, that was section 2, and we were mentioning spanning tree and all of that. So the reason Cisco and a lot of networking vendors are moving away from spanning tree is because it was never a perfect protocol. So by that, I mean, even though you could spend a lot of time and configure a spanning tree domain perfectly, and you could change your bridge IDs and your priorities and stuff, and make sure your root bridges are where they're supposed to be, and configure your interface costs and everything, you would still see a lot of spanning tree issues. That thing called reconvergence, it happened way too often. And in real networks, you saw a lot of issues with that reconvergence and with BPDUs just ending up where they're not supposed to end up, and port fast not working properly, and floods happening all over the place. And basically what a lot of network engineers said is we need to move away from these large bridge networks and these massive layer 2 links, and we need to move to layer 3 links, because layer 3 links isolate all of these broadcast storms very well, right? So you basically set up a bunch of small networks, just point-to-point networks, and then you got rid of all of these BPDUs and spanning tree protocol problems and all of that. And these layer 3 links are much easier. So all we're saying here is before we had routers or layer 3 switches, and we had networks set up on these Z switches, right? So I gave you the example. Okay, tell me if you can. It came back. Okay, yeah. I saw somebody drop just now and come back. Hearing me properly now? Yeah. Okay. Cool. Thanks. Yeah. Right. So we're talking about the list map server and these EIDs and RLOCs. So before, what we had was we had these routers and these layer 3 switches where we set up the networks here directly on the routers or switches, and we used either static routing or these dynamic routing protocols like OSPF to advertise these networks into the OSPF domain, right? Remember, we had a bunch of networks, and we had that little diagram showing that OSPF routers would have a complete map of the network. So that doesn't happen in this overlay network now. So what happens is you have these EIDs, which are these edge switches here, and you have this map server, which kind of maintains that database of the whole network. So this map server is what would map this switch and this RLOC to this network. And he would have an idea of how to get to the different locations here. So later on, when a fabric edge switch wants to know how to reach a particular endpoint or subnet, it simply queries the Lisp server, which forwards the query to the original switch that registered the EID subnet. So just as an example, we have a packet coming into this switch here, which is part of this SDA network. And when the packet comes into the switch, the switch here would query this Lisp map server, and the Lisp map server would say, hey, this network that you're destined for, I saw a registration coming from this guy before. So I'm gonna send a message, send here. So you see 3, there's a guy that coming in there, 4, the message comes here, then the Lisp map server will send the request there, and then this switch would start that communication here. So see, he will send that message directly here, and then look what happens here. So the two fabric switches then communicate and form a VXLAN tunnel to pass traffic between themselves. So they set up that tunnel dynamically here, and then they could communicate directly here. So that IP packet is wrapped in a different tunnel in UDP and then VXLAN, and then it's sent directly here. So there. So by using Cisco DNA Center along with this new SDA fabric, we can achieve entire new principles of networking. Rather than configuring security policies as a series of ACLs on multiple security devices, for example, we can configure our policies through a GUI or an API on the northbound interface of the DNA controller. The DNA controller would then handle the logic involved in configuring the SDA fabric network to match our configurations. Since our VXLAN tunnels are dynamically formed, we have much greater control over how traffic flows through the fabric network. So you see this tunnel that was formed here, that's not a physical connection, right? Before this whole process here and before the whole querying of the Lisp server and everything, this tunnel didn't exist. So this is all dynamic, which saves a lot of resources and makes this a lot more flexible. This is a much more flexible architecture because you're not limited by, you only have a physical connection here. So if you want to get traffic here, you need to bounce it through this and go here and potentially create a loop and stuff. This tunnel is only formed when the packet needs to get to there. Right? So one of the advantages that we see in here is that the DNA Center appliance controls this fabric architecture, and we have a lot of flexibility into it. So rather than working around the physical architecture that we have, we could just put in our policies into DNA Center, and DNA Center will intelligently create tunnels and create the overlay network that we want to match these policies. So we just need to tell DNA Center the policies that we want and the intent that we have for the network, and then DNA Center will remap the network as it needs to map our policies. So now that we understand the basics of how controller-based and Cisco DNA-based networks are architected, let's compare the management of both networks. Depending on which vendor and which product family was chosen, traditional campus networks may resemble a number of different models. The official cert guide has chosen to base this comparison on a product called Cisco Prime Infrastructure, or PI. So we will follow this comparison as well. Cisco PI offers many benefits, some of which are shared with Cisco DNA, and some of which are different. So just as a backdrop to all of this, this is very new and very dynamic. So Cisco DNA Center, as I mentioned, it's not in any local providers networks as far as I know. And in Cisco land themselves, they're still developing this appliance a lot. It's not a finished product that they have, perfected and it's out on the shelves a while now, and they're not making any more changes. It is a dynamic product, and even in the official cert guide, they will tell you there's a lot of changes happening. And by the time I give you this information, Cisco DNA Center might have changed a lot in the last month or 2 months. So what happened was they had this thing called Cisco Prime Infrastructure, or PI, and they used to base all of these models and all of the explanation on what you could do based on Cisco PI. And then with this new version of CCNA, they updated it and they changed it to Cisco DNA Center. So you'll see a lot of the features are the same, and they just kind of update the naming schemes as they go. So if you're interested in this stuff a lot, check out the textbook, and also just keep up to date with Cisco, because they'll continually add more and more features to this stuff. This is literally cutting edge in the world of networking. So features of Cisco PI include a single plane of gas for centralized monitoring and management of the network, dynamic discovery, inventory, and topology arrangements of nodes on the network, assisting with setup of new devices, simplified quality of service deployments to each device, assisting with the management of Cisco iOS images and updates, and management of both wired and wireless devices from a single platform. So for anybody who logged into the sandbox, you realize a lot of these features in Cisco DNA Center as well, right? We saw that we had that dynamic discovery feature. You had that single plane of gas, which is just one screen, and you're seeing everything on that one screen. You don't need to know any CLI commands to go into different sections to check different things and stuff. You're just seeing a bunch of different health checks on the same screen. And you have all of these nice features with new devices and quality of service deployment and updates and everything. Now, Cisco DNA Center also includes many of these features. For example, it includes dynamic device discovery and topology creation. So you see here, you could create your own locations like Australia and Sydney in Australia, and then different buildings in Sydney, and you could assign different devices into your buildings, because that's what we actually have, right? We have different buildings in different campuses and then different devices in the building. And we could just tell Cisco DNA Center that we have these devices in the building, and DNA Center will try to map it out for us and figure out the physical connections between these devices. And it will figure out the host name dynamically, and it'll try to bring a lot more intelligence to the network, for example. So as you can see, Cisco DNA Center is also a GUI-based application, that helps you manage the entire network just as Cisco PI does. However, Cisco has also pushed a ton of newer and better features into Cisco DNA, such as Easy QoS, which offers even better assistance to configure quality of service from the GUI, traffic analysis, which enables encrypted traffic analysis for visibility of threats, Device 360, which offers an all-around health analysis of a device, and Path Trace, which helps you discover the path a packet would take from a chosen source to a destination, kind of like a trace route. But Cisco had to rename it something fancier. Perhaps the most important feature that Cisco has been focusing on with the new Cisco DNA Center is the robust northbound API, which opens the gateway to completely different methods of network management. For example, Cisco's intent-based APIs facilitate quick and easy scripting of mundane, repetitive tasks, allowing engineers to spend more time adding value to the business and less time performing the same manual commands on a large number of devices. So this is the big plus, right? And is in line with moving towards more programming and more automation. So rather than trying to map out a network by going into every single device through SSH and doing show interface whatever or show CDP whatever, Cisco's northbound API and these intent-based APIs allow you to just write out a script that will do all of this stuff automatically and just give you a map, just like this. Just produce a map dynamically, and this is a lot easier than spending a whole day SSHing into different a large number of devices. So this is what they're going for basically. So you have your fabric network below or your underlay network. Well, remember we said the fabric was the combination of both the overlay and the underlay. So you have your fabric made up of all the physical devices that we had before. So our access points, our wireless controller, our switches, and our router, all of that is grouped to make up the fabric network. And then on top of that now, we have this Cisco DNA Center controller, which is the intelligent appliance that gives us a lot of functionality and is built on this fabric. So you have your Cisco Identity Services Engine, you have your policies, your provisioning, your assurance, your design. You have a bunch of different policies that you can throw into this controller through this nice GUI interface. And all the fabric does is it allows the packets to flow through. And that's it. All the intelligence is abstracted into the Cisco DNA Center appliance. And we saw that, right? We have a bunch of buttons and a bunch of different knobs we could turn in the Cisco DNA Center appliance, and we don't need to touch a CLI at all. And that's what Cisco is going for here. More programming and automation and more intelligent design, as opposed to what we did before, which is running around with a console cable and trying to copy and paste commands into different devices. Note that Cisco DNA Center is very much an active project, and you will likely not see it deployed in many enterprises currently. However, Cisco has dedicated a ton of resources behind their software-defined access network, and you will likely see it becoming more prevalent in the next few years as automation becomes the norm across the industry. Note that also we have discussed Cisco PI as our example for enterprise management. There exist many other solutions. Many of these solutions require a ton of manual effort, relying on console cables and SSH access for engineers to perform any kind of work. So as I said, Cisco is trying to pull out the manual effort that we are accustomed with. So we are accustomed with console cables and SSH access, and Cisco is saying no, we could automate this a lot, and that's what they're pushing for here. So yeah, more examples of the DNA center. So they'll see this is the URL that I went for, which is part of Lab 20. You can read all of this information for yourself if you're interested. But you can see the benefit of it immediately, right? This interface looks a lot nicer than an SSH window. And you can immediately watch this and say, okay, this is a switch, because a switch symbol. We can see the host name of this device. We could press on it with just a left click, and we could immediately see the IP address, what software version it's running, what type of device it is, what role it has in the network, the MAC address, the platform, and we could do a ton of different things, not just basic health checks. We could build those robust northbound APIs and the scripts that run over those APIs, and we could do a lot of intelligent things on the network. And that's what Cisco is pushing for through this Cisco DNA Center. So automation of these traditional networks was typically a pain, as many devices were not built with automation in mind. The result was that any scripts crafted were non-intuitive, slow, and inefficient, and were basically simulated SSH sessions to each device in an attempt to reduce manual SSH sessions or capture data periodically. Cisco recognized the inefficiencies of this process and is now actively developing DNA-based management to solve many of these problems. In the next section, we will discuss the introduction of REST-based APIs, which simplify a lot of these scripting tasks in Cisco DNA Center. So just to give the context here again, I have automated a lot of stuff based on Cisco devices, and it's basically SSH into this device, run this command as a robot, pull out the output, and then go through that output and try to figure out what Cisco said in return. So if you wanted to capture the bandwidth on an interface, you would SSH into the device, do a show command, get the whatever bits per second, go through all the output to get those bits per second, and then throw it in something that could map it. So those NMSs could do that. SNMP, sorry, was another useful protocol, but it was kind of difficult to understand because they had that big MIB and those large OIDs. That made it kind of difficult to figure out what you wanted. So the whole point of these APIs and Cisco DNA Center and a lot of these new automation platforms is to make that process a lot easier. If you have 100 switches and you want to monitor bandwidth on each one of them, you should be able to just click a few buttons and produce a big graph that can show you the bandwidth, the throughput of all of the interfaces on all of the devices. That shouldn't take a lot of scripting to SSH into a bunch of different devices, because that's very slow and inefficient. So let me go through some of these APIs now. So we've mentioned APIs frequently in the preceding topics, but we're going to really dive into the definition and structure of them now. So an application protocol interface, or API, or an application programming interface, as it's sometimes called, is a method for one application or program to interact with another application or program. On the surface, if you have no programming experience, it may seem confusing or over-engineered, but you should have already begun to see the need for APIs from our previous discussion. For example, once upon a time, routers were designed as black boxes, with manufacturers keeping the code running the routers closed off and only allowing engineers to access particular configuration files and physical interfaces on the router. So going back to my example, if I wanted to log into a Cisco router and figure out what's the current bandwidth on that router, the only way I could do that right now is through SSH or through SNMP. So there is no way for me to go and write a Python script and have my script say, hey, code running on the router. I am some fellow code. and I want to know this thing. Can you give it to me in a nice format? The router is a black box, right? It is closed off from all other programs outside of that router itself. It is a closed off box. So APIs allow programs to talk to each other. So a program in a router could talk to a program that I write, or a program in Cisco routers could talk to a program in a Juniper router or a Fortinet box, for example. And you could have code talking to other code, which is very important. So however, with the advent of SDN, controller-based networks, and increasing automation, the code behind routers and all other infrastructure components now needs to become very dynamic and open. Now, rather than each manufacturer writing their own proprietary code and having that code run in isolation, manufacturers also need to consider interactions with code in other platforms. APIs facilitate these interactions. Once a developer creates an API for their application, other developers of other applications can then consume or utilize that API to interact directly with that application. So just as an example again, a Cisco engineer might write 1,000 lines of code to run some function on the router. Okay, cool. On my end now, I want to say I need to graph out some useful stuff on that router. So I want to know what your CPU usage is. And I have a nice graphing application that wants to interact with that router and pull the information from it through code. An API is what would be running on that router and would allow me to query the router and say, every 5 minutes, give me your CPU usage. So I could push that into a graph very easily without having to manually go in and do show CPU usage or whatever the command is. So representational state transfer, or REST, or RESTful APIs, are a group or category of APIs that follow a set of 6 guidelines. So we mentioned APIs before, and now REST is just a category of APIs or a subcategory of all APIs. REST is a particular type of APIs, basically. So REST APIs follow a client-server architecture. So one application hosts the API and handles requests, while multiple clients may consume the API by sending requests to the server. The REST APIs also follow a uniform interface, so resources on the server should only be identifiable through a single URL and should only use standard methods of the underlying protocol. REST APIs use only stateless operations, so all client-server operations should be independent of any other operations that occurred previously. They should utilize resource caching, so all API calls should clearly mark which resources are cacheable and which are not. They should be built using layered architectures, so APIs should be layered so that distinct functions can be modularized and scale better, and they should supply code on demand. APIs should usually return data in a serialized format, for example, using JSON or XML, but they can also supply code or applets when required. So these are just like the guiding rules for REST API developers. They need to follow these tenets or these commandments. And once they could ensure that they check all of these boxes, then they have created a REST API. So to understand many of the concepts in the following sections, you need to be familiar with a few programming concepts. So you don't need to become a master programmer, but some of the terms that we're going to use to describe REST APIs will only make sense if you understand a little bit about programming. So that's why I include this backdrop here, right? So a variable is simply a container that can store a value. This value can be changed throughout the life of the program, and variables are identified through their names. The following snippet shows some variables that are declared and immediately assigned values. So this looks like Python, but variables are used across all codes. C, Java, Python, Go, whatever it is. All programming languages have some method of creating variables. So you can see here we create a variable called x, and we assign it a value of 3. Which means that we have some piece of memory in this machine, and we call that the location in that piece of memory x, and the actual value that it holds in the container is 3. Then we create a next block of memory or a next container, and we call that container y, and then we assign or we put in the container the value -4. Then we create a next container or a piece of memory, and we call that z, and we put in the value, this 1.247, into that container. And we could store a number of different things in these variables, right? Or these containers. We could create a container called heading, and we could store this big string into there. The product is whatever. And then using these variables, we could perform functions on them. So we could say, we have something in X, we have something in Y, we want to multiply X by Y, and we want to know the value of things in those variables. So variables are just like containers or pieces of memory, and we could throw values into them, and those values could change. So that's it for the programming. We just need to understand what a variable is. It's just a container that can store a value. Now, sometimes variables are not this simple. We may want to collect data on an object which has multiple fields. For example, we may want to create a list of all interfaces on a router. For this, we expand our simple variables into data structures, such as lists or dictionaries. Just in the Python world, we have these things called dictionaries. Since Python is one of the most popular languages used in scripting and automation, we will make many references to it. So that's why I use Python here. You'll see in a lot of those Cisco DevNet labs, they use Python as well, because it is growing to be one of the most popular automation languages. So the following snippet illustrates examples of lists and dictionaries. So I have list1 here. So this is our container, but our container isn't just list1 equals 2, right? We have list1 is equal to, and we have these square brackets here, and we store in multiple values in this container now. So this is called an array in Java, but the concept is the same. So rather than storing one fixed value, we store multiple values in this container or in this variable. And then expanding from that now, we could also create something called a dictionary in Python, where instead of just having these random values, we could assign them keys. So this will make more sense in the context of routers, right? So for example, this might be interfaces. So you have interfaces on a router. We obviously have multiple interfaces. It's not just one. So you see, we won't just have gigabit 00 on our router, right? We have multiple. So you can see why we would need a more complex variable to store all of the interfaces on the router. But also, this interface here wouldn't just have one property, right? Interfaces have different things on them. So you have your configured speed, your configured duplex, your configured IP, your description, what else? The actual what do you call it? The status of the interface, whether it's up or whether it's down. You can think of a bunch of other things we get when we run that show command, right? So we have different properties that will belong to this interface now. And these variables allow us to store those properties in intelligent ways. So rather than just listing out the properties, dictionaries in Python let us name those properties. So this is called a key, and this is the value of the key. So you have the key called configuration speed or configured speed, and every single interface will have a configured speed, right? Whether it's auto or 100 megs or a gig or whatever it is. And we know what the auto is here because we named this key. So when we see this dictionary and we see something called config speed, we kind of know just by reading it and reading how nice is worded here, we kind of know what this value of auto represents. If we had blocked out this and this was just like 0 or 1, we wouldn't know what this auto is, right? If you saw a list and it said auto 10 1 1 1 1, you wouldn't know what you're already reading, right? But if you see config speed auto, config duplex auto, config IP 10 1 1 1, then you know, okay, this kind of makes sense. This stores some properties of our interface, and this auto is the configured speed, this auto is the configured duplex, and this IP is the configured IP. So you can see how we get intelligent with variables, and we know what we stored. When we stored a value, we didn't just store it under some random thing. We stored it in a way that makes sense. And this whole concept is going to be very important when we describe REST APIs and when we read something called JSON. So now that you understand some basics about variables, let's get back to REST APIs. Most applications written perform the following 4 main functions. So you have something called create, which allows a client to make new instances of a variable and assign values to them on the server. You have a function called read, which allows a client to fetch values currently assigned to variables as already created on the server. Then you have update, which allows a client to set new values to variables that exist on the server. And then you have delete, which allows a client to remove variables previously created on the server. So developers commonly refer to these as CRUD operations. So the CRUD there, CRUD, create, read, update, delete. Those are like the four main actions that we want to perform on variables. So here we saw really the creation, right? So we create those variables and we either just create them or we create them and assign values to them one time. But that's all creation there. Later on, we would want to read these values to get back the value that we stored in there initially. We may also want to update it. So for example, if this IP changes, we may not want to delete the whole variable and start over. We might just want to update this value here and change this IP to whatever the new IP is. But we also have the option to delete it. So if the router is ever taken out of production, or if the router dies or something, we may want to delete that variable. So we have the option of those four actions there. So while REST APIs could theoretically use any protocol of their choosing, most REST APIs use HTTP, as it matches many of the principles of REST APIs that we discussed before. So that same HTTP protocol that we use for web pages, REST APIs make use of that protocol. So HTTP uses actions or verbs that mimic these CRUD actions. For example, an HTTP GET request allows a client to fetch resources, like a web page, from an HTTP server. This HTTP GET request is sent from your PC to a web server whenever you issue a request to load or read a web page. The table below shows some other important REST or HTTP verbs. So we have our CRUD here, right? So we have a good idea what CRUD is now, and this is the action that we want to do. We want to create new structures. We want to read the variable names and the values. We want to update the values, or we just want to delete the whole variable. And we know how that corresponds to CRUD now. But in the HTTP world, we have different names for them. So the first one I started off with is GET. So if you want to pull, if you want to get to your Facebook page, HTTP is going to use that action or that verb called GET. If you want to update something on a page, you're most likely going to be using a post. If you want to create something on a page, you're going to be using a post. So like if you want to create a new Facebook message, or if you're setting up a new variable on your router, you're using this verb called post. If you want to update, you could use this patch or this put. And if you want to delete, you just use the word delete. So that one is easy to remember, right? But this is the actual implementation on HTTP of how we implement these CRUD verbs here. So you need to memorize these different words. So Cisco might ask you, you want to set up a new variable using REST APIs. What HTTP verb are you going to use, or what HTTP action are you going to use? Yes, no, post. So just like we issue HTTP GET requests for URIs of particular web pages, for example, www.google.com, we issue a REST API request to particular URIs. Different URIs are associated with different resources on the API server. So just as an example here, you have our protocol here. So HTTP or HTTPS, and then you have the actual host name or address, and then you have the path or the resource. So this is the main host name or the main address of the server. But then to access a particular set of variables on a particular device, we go down the path. So DNA, intent, API, version 1, network device, whatever it is. It could be different. So we start off, for example, we could start off with google.com here. And then if we want to retrieve a particular page from google.com, we could do google.com / and whatever query you put in, and then maybe like a 1 for page 1. If you ever do a Google search, just look at that URI and you'll see it kind of resembles this. And REST follows the same sort of structure. So once we issue a correct REST API call, we will be presented with variables and data in a particular format. Often, this output data will utilize a particular data serialization language. These languages allow the API to represent its data and variables in a standardized format, such that other applications can easily read and import the data. This lets us easily create variables in our client based off the outputs of the REST server. This also lets us store data in a standardized format so that it is easier to read at a later date. We will explore a particular data serialization language that Cisco has identified called JSON in our last topic. So there are many languages that we could use here. The serialization languages, I mentioned JSON and XML. We're going to talk about JSON in particular because Cisco just chose JSON. And it is very popular. So I have no problem with that. Learning JSON is useful, but it's not the only language that you could use for this. It's not to say that all REST APIs have to use JSON or all APIs have to use JSON. They could use XML. They could use a bunch of other things called data serialization languages. So this is what we're talking about here, right? This is the whole process of what we're trying to do. So we have this REST server and we have this REST client. So in the Cisco world, you could think of this is one Cisco router and this is another Cisco router. So the code that runs on both of them could be like this purple outline here. So that's their internal code. Before the whole API and before the whole JSON, they just had internal variables. So Cisco might have named their variables like router interface 1, router interface 2, router CPU usage, whatever it is. They had those blocks of memory in their code, and they stored everything internally. But without this API and without this JSON and stuff, they had no way to get those values out of those internal variables and into another code, into another program that somebody else had written. Now with the APIs, we have, once you set up a REST server and once you set up an API on that server, you'll have this API layer here, and then you could output a JSON string. And then your client will make a request for that JSON string, and you'll see your values go in here. The JSON string will be read into your program, and then on your client, you could convert that JSON format because it's so standardized and it's nice to read for both humans and machines. And you'll see an example in a little bit. You could convert that data and make your own variables off of that. So this client, for example, this could be something like SolarWinds or Zabbix or Cactus or whatever. Sorry, Cacti. And you could read values through this API off of your routers, and you could create your own values in the SolarWinds server or in the Zabbix server as it stands. And you could dynamically read this. So the big advantage of this is you could query router CPU every 10 seconds if you want. You don't need to SSH and do a show command, and you don't need to waste time doing all of that. You could just perform this thing as many times as you want, as quickly as you want. And it's very, very quick and efficient to read these values off of the router. So that's it for this class. I know I covered a bunch of topics. We will cover more of them and we'll keep discussing them when we go into the last two topics. I'll show you an example of the actual JSON, just as a little teaser before Tuesday. And when you come back, we're going to start our first non-lab lab, I guess, which is the Fortinet Tennessee one. So that's the first bonus course we have. I'll get you started. It'll just take like a 10 or 15 minutes, and then you just have to spend like an hour watching videos. But we'll discuss that after the break. So let me check back. You can check my back like 7:05. Yeah, 7:05 should be fine. Shouldn't take too long. Right. 1 second. Share back the screen. Okay. Hopefully everybody back. I'm gonna send them a message there. Right. I need to write. Okay. Cool. So I didn't put this in the slide because it's not strictly Cisco related. But what it does give a good example of what we're talking about. So this is my personal website that I developed in just to learn programming and stuff a lot better. So look at the URL here, right? It's a very common, I am sharing my screen, right? Yeah. Yeah. It's a normal common URL, like you would put google.com, and you can see, we have a taskbar and you have images and everything, just like a normal web page, no problem. Now look here. So you don't need to put the word API. I just put it in because it makes more sense to me. But the actual API endpoint is this. So we expand the URL and we add in a little bit there. And instead of getting a normal HTTP page like this, we get this thing. So you'll see here, everything kind of named intelligently. So I have this thing called the Django REST framework, which is what I use in the backend to build this API. And it kind of intelligently shows the data that is in this API, right? So this is the actual data here. So you see there, I put a GET request. Remember those verbs that I discussed? So I put in a GET request by just putting in this URL into my browser and pressing enter. I submitted an HTTP GET request to this endpoint, which is that same thing there. And this is the response. So HTTP 200 OK. It allows get, header, and options. This is the kind of content it's responding with. So you see application JSON. So that's our JSON data there. And this is the actual JSON data. So you see it kind of looks like the variables we were talking about before when I showed you the screenshots of Python. And you can see these nicely labeled keys and the values here. So date, there's the date, and then the country name, whatever it is, and the total COVID cases, new cases, total deaths, new deaths. So even if you didn't know what my website was doing, you could kind of read through this and you could immediately see what I'm trying to build here, right? So if you pull this into your script or into your Excel sheet or whatever it is, you could take this data and graph it out very easily. Just by reading through this data. You have no other documentation, but you could just read through this and you could understand what it is you're getting, right? And that's the whole advantage of REST APIs and this JSON data. So they allow you to, well, they allow humans to read the data and understand what you're reading fairly quickly. And we'll discuss that more. So that's the last topic here, interpret JSON encoded data. So before I even give that presentation, I'm sure you could read this data and understand what you're reading, which is basically the whole that whole last topic there. You could read this name of the key and then the value of the key, and you could understand what it is you're reading. Yeah, so this is just my example of an API there. There are tons of APIs. I'd find the next cool one, let's see if I could find one. Joke API. I don't think this one actually shows you in an API format on the web page. Yeah, so they also named it API. But yeah, it doesn't show you actual example on the page. So if you put a pull request or you use in Lab 20, we had used something called Postman, which is an next application to submit API requests, and you'll get back something like this. So there's the ID of the joke, there's the actual joke, and there's the status. So you see there are a bunch of different APIs. Just Google around if you're interested. And that Lab 20 will give you some tools that you could use to consume APIs. So like this, you could use the same URL here and that Postman appliance, so that Postman application that you had to install for Lab 20, and you could get something like this. And if you keep submitting more and more requests, you'll get random jokes like this. So I thought this was a nice tutorial for it. Right, so that's it for the class today and now for the lab. Right, so as I mentioned in the last class, we finished with the normal Cisco packet tracer labs, right? Lab 20 is kind of a bonus lab and kind of a segue into section 6. If you could actually get everything installed and do that sandbox lab, it'll be very beneficial. But that's it for everything Cisco wants you to learn to configure. So we're going on to the special CFSI bonus courses now, and we're going to start off with Fortinet NSE1. So before I start, as normal, I'll give the context. I am not a Fortinet expert by any ways. I got to work with a lot of vendors, but not Fortinet. It just so happened that I never end up in a Fortinet company yet. So the NSE1 and 2 just kind of give you general security concepts, but they don't really put you into a Fortinet GUI or a Fortinet CLI and show you a lot of configuration options, right? So you'll see it is a really easy course, and you can do it in an hour. It just kind of shows you different security concepts. So just to expand on it, I'll give you a little background into Fortinet for anybody who hasn't heard of the brand, and what you can do if you want to become a Fortinet expert. So who or what is Fortinet? Fortinet is a cybersecurity company headquartered in California, USA. They manufacture cybersecurity software and hardware, including such appliances as firewalls, switches, sandboxes, and traffic analyzers, and such applications as anti-spam, antivirus, and security information and event management software, or SIEM. So this is an example of what a physical Fortinet appliance looks like. So this is a firewall, and this is a switch. So you see the nice logo here, and most of their boxes is white, and they have these nice grill patterns in front. So Fortinet has been gaining traction in the cybersecurity market recently, being awarded such awards as Network Security Company of the Year for 2019. So that was our awards function in India. And locally, many ICT companies have been bringing in Fortinet appliances and asking for qualified individuals to operate them. So Digital Business achieved Gold Partner status with Fortinet back in 2016. So this is just a little article I found. Digital have a bunch of different teams, and I didn't end up on the team with Fortinet stuff. But the point is, a lot of local companies use Fortinet, so it does make sense to pay attention to them and to get certified or qualified if you're interested. So chances are good that more ICT teams are going to adopt Fortinet solutions soon. Therefore, in this class, we are going to get you started on your Fortinet journey. In 2014, Fortinet introduced their Network Security Expert, or NSE, Technical Certification Program. Using this program, you can both gain an introduction into Fortinet's suite of appliances and also prove to employers that you can operate their shiny new Fortinet appliances. The Fortinet NSE program is currently an 8-tier program with the content and requirements increasing in every step. More than 200,000 NSE certifications have already been issued. NSE certifications are valid for 2 years from the time they are passed. Candidates are encouraged to continually study and move upwards on the NSE chain to ensure that they stay relevant in the global cybersecurity landscape. So this is what it looks like, right? So you start off at NSE1 at the bottom here, and you see the different descriptions there. Develop a foundational understanding of the ever-increasing threat landscape and general network security concepts. And then you develop some knowledge about the Fortinet solutions for addressing these threats. NSE3 is just a sales certification. So I don't know why they put it here and why they didn't split it off. But basically, the jump is supposed to be NSE1 to 2 to 4, and then you keep going up from there. As far as I know. I don't know anybody personally who has reached 6 and 7 and 8. But definitely you skip 3. Skip 3 is for sales associates for some reason. So in this class, I'll show you how to get 1 and 2. And then if you're interested afterwards, you could study and go on to 4 and build up from there. So this is the next guide for it. So in NSE1, for the security associate, you just have to pass all lessons and quizzes, and you'll get a PDF of the certificate. For 2 is basically the same thing, just a bit more videos to watch, and you'll get that NSE2 certificate. 3 is sales training. Again, I don't know why they stick this in here. but they did, so that's it. So you skip in 2 and you go into 4. And 4 is the actual exam in an exam center, just like Cisco. Sure, now we have our online version for it, but it is an exam center exam, as opposed to 1 and 2, which is just watch videos online and you get a certificate in your profile online without having to write any exam. And you can keep going there. So if you're interested in the Fortinet line, you'll have 2 by the end of this class, and you could take your time and jump to 4. It is an in-demand cert. So this is just an estimate of the amount of time that it would take. Yeah, the 1 hour seems about accurate. I don't think you should take 4.2 hours for this, more like 2 hours or 3 hours maybe. But you'll see. And then yeah, these are way more time. So you'll likely, if you're definitely interested in Fortinet, then you'll have to take your time and go through these things. So go to pearsonview/Fortinet or this Fortinet URL to learn more. So for now, let's get started with the NSE1 cert. So, well, this is what I'll leave you with. You basically need to go to our URL and create an account. And then, you're doing your sign in after you create your account. Then you should see a page like this pop up, and you go into library, and then NSE1 here, and you'll see this thing here, which are just 12 self-paced activities or 12 videos that you need to watch. So you're clicking on these 12 self-paced activities, and you'll see this kind of description page come up. So make sure you read this properly. So the important thing here is the passing score. And then they'll tell you how to get the certificate. It usually takes like an hour or less in my experience. After you finish all the videos and you complete all the requirements, after like an hour, they'll usually give you your certificate with your name and everything. So you can print it out and put it in your portfolio. So you just start off there with each module. Yeah, with each module, you'll get a video to watch. Make sure you watch all the videos straight till the end, and you'll get this check mark. And then click the quiz, and you'll just need to do a little multiple choice quiz. So make sure you pay attention to the videos and write down the answers if you need to. And once you finish the quiz, well, yeah, once you finish the quiz there, and you get a check mark, lesson 2 or the next module or the next section will open up. And when you reach the end, you'll see the certificate prompt. This is how the video will look, and this is how the quiz will look. Yeah, so just play the video right in your browser there. Make sure you watch the whole thing and make sure you're paying attention to what they're describing, and then you'll get the answers to these these quizzes from the video itself. And then you'll get your certificate here at the bottom. It's not a badge like this. It's actually a full certificate with your name and everything. So don't worry. That's it. I think that's it. Yeah. So take your time. This should be the easiest lab you do in this course. And it's a free certificate. So go ahead and take a try. So that's it for this class. I will see you all next week. So make sure you have NSE1 by then. You really shouldn't have any reason not to get this. As I said, the certificate might take a while to reach you, but at least finish it out and check back the next day. And ask me about Lab 20 if you have any questions. That's it. Let me stop recording.